Hey there, everyone. This is the last video talking about the APPC exam, and this is dealing with the rotational inertia integral. As I mentioned, this is actually the one part that, regardless of whether you've taken calculus, you definitely want to make sure that you go over this video. This is actually the one part that's really tough. I'm going to talk about how to set up the rotational inertia equation, how to deal with this DM term, how to solve it, and then how to approach the same problem using what's called the parallel axis theorem. So, for the most part, mentioned before that the integral equation for the rotational inertia is given like this: the integral of r squared with respect to dm. And as I mentioned before, that there is a relationship between r and m, and we have to make sure that we reflect it in our equation. Now, the way that we're going to do this is a little bit different. First, we're actually going to use a very similar trick that we did in the gravity and circular motion unit, where we talked about how when we change the radius of an object while keeping its density the same, we found a way to find the mass by using the concept of density. We're actually going to do the same thing here, but we're going to use what's called linear mass density, mostly because of the fact that the problems that you're dealing with where you're going to have to do this are going to be typically rods that may be rotated at a different point than what we're used to, or maybe it's going to be a rod that has a slightly weird way that the mass is distributed. Now, the linear mass density is represented by the symbol lambda. Lambda, just like with density, where the density was equal to mass divided by volume, because this is a linear case, it's going to be mass divided by r, or length. Now, we're going to rework this equation to look like this: m equals lambda r. Now, what we're going to want to do is our integral is in terms of dm right now, but I don't want it in terms of dm. I want it in terms of r. So what I'm going to do is I'm going to differentiate this. So this becomes dm equals lambda dr. Now, I do want to note one thing, is that this is right now assuming that the linear mass density is constant. It's uniform, meaning that the mass is uniformly distributed across the object, like a ruler. We're not talking about a baseball bat. If the object was varying in its density, so there were sections where it was heavier and sections where it was lighter, what we would have to do is we would have to be given what the equation is for lambda as a function of r. And then we would have to put that in when we go to differentiate. So we basically take the derivative. But this is going to be the more common thing. That's why I want to do this. The likelihood of you seeing lambda as being some function is very rare. So we'd end up with this equation: dm equals lambda dr. And then what we're going to do is plug in for dm this term. So our original equation, which was integral of r squared dm, now becomes integral of r squared lambda dr. Lambda, again, because this is uniform, it's constant, can be pulled out of the integral. So we end up just taking the integral of r squared with respect to r. Now, this is a polynomial. We all know how to do the integral of a polynomial. So from here, it's easy streets. So I add 1 to the exponent, I divide r by 1/3, and then with this lambda 1/3 r cubed. Before I continue, I would then have to plug in for lambda the original equation, which remember was m over r, to get 1/3 mr squared as our final answer, because we'd have mr squared, because the r cancels out one of the r's in the cubed. Now, is that it? Not yet, actually. There's something I forgot to mention. What I mentioned is, how are we going to deal with bounds? So for the most part, they're going to tell you where the object is rotating. And that's something you're going to have to keep in mind: is where is this object rotating from? And that is going to give us our bounds. Now, one thing to keep in mind is that the center of rotation is going to end up being considered 0. And then we're going to have to find out where the two ends of our object, in this case, let's assume that it's a rod, where the two ends relative to the center being 0, the rotation being 0. A perfect example is this. Let's say that we had some beam and it was made of length L, and we're going to rotate it at a point that was a quarter of the length away from the left edge. So it's halfway between the left edge and the center of the object. Well, at that point, because the left edge is to the left of it, I would say that it's negative 1/4 L because it's to the left of where my rotation is. The other end is 3/4 of the length away from that point, so it would be a positive 3/4 L. So this is kind of the part where it gets really weird, is determining these bounds. Now, we would set up the integral the same way, with our bounds now being 1/4 L and 3/4 L. However, one thing we have to keep in mind is that before we replace lambda, we have to evaluate the bounds. So again, we go from 3/4 negative 1/4 L to 3/4 L. So we plug those two numbers in for R, again, before I replace lambda. So I plug it in over here, I plug it in over here, subtract the two terms just like we did before. I end up getting this really weird equation, 7/7/48 lambda L cubed. Now that I get to this point, I can then take it that one step further, replace lambda with m over L, and the L's cancel out, and end up with 7/4 ml squared. Now, next question that you might have to ask is, do I have to do calculus? And the answer is not really. You don't always have to do calculus. There are some questions where they will explicitly say that they want you to set up an integral. They sort of walk you through the process a little bit. So there's a little bit of ways that you can kind of uh, cheat out a few extra credit points, or you could cheat out some partial credit points, I should say, not extra credit. But for the most part, you don't have to always do it. You just have to be very careful that it doesn't explicitly specify that you have to use calculus, and you have to know where what the rotational inertia is around the center of mass. So a lot of times, if they give you this rotational inertia around the center of mass, that's kind of the hint that you're being allowed to use the parallel axis theorem. Parallel axis theorem is essentially how to figure this out using algebra instead of calculus. So the equation for the parallel axis theorem basically states that the rotational inertia around any point is going to be equal to the rotational inertia around its center of mass plus mr squared. So that's what ICM is. ICM is the rotational inertia around the center of mass. Like I said, you tend to have a lot of common examples. So you know what the rotational inertia is for a beam around the center of mass. You should also know it for like a sphere around the center of mass because they're just very common. But you don't have to memorize them because they're usually going to be given to you. Now, what is the mr squared talking about? Well, first, as we mentioned, when you have an object, the center of mass can almost be considered as if like that's where the object is. Like we can take this a long beam and almost condense it to a ball where all of its mass is at the center, uh, at at that center. So the mr squared is what is the rotational inertia of rotating an object some distance from that mass, and that's what this is. You don't really have to worry about it too much, but it's just taking into account the location of the center of mass from the rotation of the object, the center rotation. So let's go back to our previous example where we had the beam of length L being rotated at a quarter of the length L from the left edge. Well, for a uniform beam, you would most likely be given that the equation for around the center of mass is 1/12 ml squared. So we already know what ICM is, easy enough. What do I do for mr squared? Well, I know what the mass is, it's m. I mean, the question doesn't explicitly say it, but again, it's just a sample problem. And we know what the distance is because it's 1/4 the length away from the left edge. We know it's also 1/4 the length from the center, which is halfway. So we know it's 1/4 the length from the center of mass. So I plug in 1/4 L in for R, and that gets me 1/16 ml squared for that second term. So I just take these two parts and add them together to get 7/48 ml squared, the exact same equation that I got before. So if you are forced to do the calculus form, you could always do the parallel axis theorem as a way of knowing what your final answer is supposed to be and then trying to find a way to work it out that way. Uh, that's pretty much it. Like I said, this can be a tricky part. You're definitely going to want to make sure that you find some free response questions that you can work through and see what you have to do. One thing to keep in mind though is that a lot of times just setting up these problems can give you partial credit. Even if you aren't sure exactly how to plug in anything for R, try something because using this equation of ICM plus MR squared can get you a point. Knowing where like that this is ICM can get you another point, and then finishing it off can get you a third point. So you might be only missing one of those 4 points by not exactly knowing what goes in for R. So this again goes down to the practice. You want to practice to know where are you supposed to be. What are the things that they're going to be looking for when you're solving these problems for the parallaxis theorem? And you want to make sure that you have those parts down packed. And you want to know when you're supposed to use the parallaxis, when you're supposed to use calculus, and when you have the option to pick. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.